Good morning, everyone. It is a great pleasure and an honor for us to host today Professor Nirenberg, who is the recipient of the Abel Prize 2015. It's the second time that an Abel Prize visits this School of Mathematics and Statistics after the visit that we had of Professor Michael Attia in, I think, 2008? So this visit of Professor Nirenberg has been organized by a former student of him, which is Professor Xavier Cabré, which is very well known here because he teaches partial differential equations for undergraduate and graduate students in this school. So thank you very much, Xavier, for organizing this visit. Thank you very much, Professor Nirenberg, for visiting us. It is a great honor for us. And thank you, everybody, for coming to this, I guess, very interesting conference. And now let me introduce the people who is with me here. To my right is Oriol Serra, which is the head of the Department of Mathematics. To my left is the president of the university, my former PhD advisor, Rick Fossers, and of course Professor Nirenberg and Xavier. So enjoy this conference, and I think that Professor Oriol Serra would like to say something to us.
Thank you, John. Just a few words. As we know, there is a new department in this university, a Department of Mathematics, coming from 4 departments. And the goal of this fusion is to set ambitious academic goals. And I think that this today illustrates very much what we want to say by ambitious academic goals. One thing that we wanted to do is to set up a colloquium, a mathematical colloquium here. And I have to thank particularly Marcel Guardia, Gilles Monguet, and Paul Rouet, who came to us with the idea and the will to coordinate this colloquium. And we had this wonderful starting of this colloquium by this occasion today. So I want to say that we are extremely happy about this, and extremely happy to the School of Mathematics, with which we are working very closely together, and extremely happy we accepted to come and to Xavier for organizing it. So thank you very much.
So now Xavier Cabré will introduce Professor Nirenberg and the talk.
So I will use some transparencies. Maybe we would like to turn. Yeah, maybe you can come here. How do I do this? No, I'm gonna. Just some few transparencies to present Professor Nirenberg. So, okay, that you know that I think I can speak. Yeah, he got the Abel Prize for together with John Nash, sadly dead right after receiving the prize. And both received it for striking and seminal contributions to the theory of nonlinear partial differential equations and its applications to geometric analysis. This is Louis some years ago. Bachelor degree from McGill University. In fact, Louis is Canadian. He was born in 1925 in Hamilton, Ontario. in the Jewish family. But he did, after the bachelor, he did already his master and PhD in New York University. The PhD is 1949 under the direction of James Stoker. And since then, he's been always professor at the Courant Institute of Mathematical Science, which is the math department of New York University. He's still emeritus professor. He goes to seminars every week there. He retired in 1999. This is he is Richard Courant, who founded the Courant Institute. That's why his name. This is the new building that dates from 65. I think Louis told me 1965. It's in a very nice area of New York, so I had the chance to to be there for 5 years. This is the building, right? And this is Stoker here? No. Stoker is not here, who was his advisor, but somewhere Louis says that he was closer, in fact, mathematically to Friedrichs, who was a very important mathematician in the field of PDEs. He settled many things back then, basic things in PDEs. Louis was director of the Courant Institute for some years, together with Lax and with Raghu Baralan, who is still a professor at Courant. They are all three Abel prizes. So the Courant Institute is the institution that has more Abel prizes. Jürgen Moser was also a professor. I had him as a professor, and he had been a faculty at the Courant. Here is James Stoker and Louis. And as we said, the PhD was 1949. The title is The Determination of a Closed Convex Surface Having Given Line Elements. This was a geometric problem. Was it the problem, the Weil conjecture already? Yeah. So his thesis solved an important, very easy, simple, easy to state problem in differential geometry, very simple to state about, in differential geometry, about curvatures. Again, Friedrichs and Courant. Louis had many students. How many?
45.
46. So it says 46, but that's wrong. 45. Which one is wrong?
I don't remember. That's good.
Okay, but there is one that is not. I hope I'm okay. I'm the third last. Well, that's number of students. That's number of descendants. Probably more than that. He has about 200 papers and more than 10,000 citations. These are his collaboration. Most of his papers are in collaboration. He says here, one of the wonders of mathematics is you go somewhere in the world and you meet other mathematicians, and it's like one big family. This large family is a wonderful joy. And Massinet makes larger names for more papers together. So you see that his main collaborators in terms of number of papers are Luis Caffarelli, Henri Berestiti, Chaim Prezis, Yan Li, who was his professor at Rutgers and was a student of Louis, and Joel Sprague. And a list of awards, the Abel Prize, a very important prize 5 years before the Chern Medal, the first one in China, the Crawford Prize 1982, this is not in chronological order, the Steele Prize of the AMS 1994, the Jeffrey Williams Prize in Canada 1957, and the Booker Prize 1959. And finally, just let me tell you that his main contributions in mathematics are the theory of PDEs, but starting from his thesis, he solved an important problem in differential geometry, After that, he also worked in complex analysis. There is a famous Nirenberg theorem. He also worked in complex Monge-Ampere equations. In real analysis, there is a very important inequality called the John Nirenberg inequality, and a very famous, very important space, which is the bounded mean oscillation, functions of bounded mean oscillation, and that's due to him with Fitjorn. And in harmonic analysis, this is a very important space. And after you talk, I want to ask you about about that. And in PDs, pretty much everything. Regularity theory, inequalities, estimates, Monge-Ampere and fully nonlinear elliptic equations, free boundaries. He has, together with Caffarelli and Sprague and Robert Kahn, what is supposed the best result in the Navier-Stokes equations, which is a millennium problem still now. Symmetry theorems, the moving planes and the sliding methods, maximum principles, front propagation, etc., etc., etc. So with this, I finish my introduction. Thanks, Louis, for being here, and we are looking forward to your talk.
Sì.
Perhaps I don't need the microphone. Can you hear me?
Yes. Okay, we'll leave it here.
Yeah, okay, just in case.
Here.
Yeah. Well, I must say it's a great pleasure for me to be here, to visit Polytechnico and to be in Barcelona, especially in this beautiful day. I want to thank Xavier and Professor Fossas for the very kind invitation. It's really a true pleasure. But I must say, during your wonderful introduction, I was reminded of a very old joke of I cannot resist telling jokes, so forgive that. It's about a teacher who is sitting at the table surrounded by his young students, and he has fallen asleep. And the students start talking about him. One of them says, "Oh, our professor is such a wonderful person, he's such a kind person." And the next person says, "And he knows so much, and he teaches so on." And so it goes around the table, and at the end the professor lifts his head and says, "Nobody said a word about my modesty." So, the talk I'm going to give is a very, I believe, expository talk, and it's not based on any new work, because I have no new work to talk about. So it's based on some old work, but it's to give an illustration of how simple ideas can sometimes be used to give proofs in mathematics. And in addition, I will present a number of open problems which have intrigued me for a number of years. So here is an outline of the talk. So first, maximum. Everything is based on maximum principles. There are various formulations. I'll present several here, and I'll talk first about I'll be using the method of moving planes, which probably some of you are familiar with, but perhaps not all. And I'll talk first about a geometric problem where the method was first introduced by a Soviet geometer, A.G. Alexandrov. I should say, please feel free to interrupt and ask questions, and to kibitz, if you know that expression. So I'll be talking about a geometric problem and then an extension of that, and the method of moving planes and sliding method of it, and then I'll conclude with some open problems. So here's the maximum principle. You are all familiar with the maximum principle for harmonic function in a domain. That means the sum of the pure second order derivatives equals 0. And if you look at a bounded domain, I always mean an open connected set. Then the maximum principle says that the maximum of a function, maximum of any solution, occurs on the boundary. But it's also very useful to know that this is true if instead of the equality you have an inequality. If the Laplacian of u is greater than or equal to 0, the same conclusion still holds. And it's true for more general so-called elliptic equation. Here's a general second order equation with variable coefficients. And ellipticity means that this matrix is strictly positive definite. That's that expression. And the other coefficients are supposed to be bounded. And that's what I call a uniformly elliptic equation. And there are different forms of the maximum principle. So here is one form that if you have a solution of the inequality, L is that second order linear elliptic operator, you have a solution of the inequality, and if the lim sup as you approach the boundary of the u is less than or equal to 0, then the conclusion is you say that the L satisfies the maximum principle if you conclude that u is less than or equal to 0 in the domain. It's not always true. For example, if you have this very simple function u equals sine x on the interval 0, pi, and satisfy that simple ordinary differential equation, it's 0 on the boundary, but it's not 0 inside, of course. It's not less than 0 inside, it's in fact positive. Excuse me. So it's not always true. So here's this simple counterexample shows that. Let's see, look at the time. Yes. There are different sufficient conditions for the maximum principle to hold. I recall the operator, this is the operator, and the C is that coefficient. And a sufficient condition for the maximum principle is if the C is less than or equal to 0. Another sufficient condition is if there exists a positive function in the closure of the domain satisfying the inequality, and then it's easy to see that you have a maximum principle by considering the function u divided by that positive function. It satisfies such an equation, and the 0th order term is that, and if LG is less than or equal to 0, that's less than or equal to 0, so you're back in that condition. So you have the maximum principle just using that condition. I repeat, please feel free to interrupt and ask questions, because everything is meant to be very understandable. Another sufficient condition, if the domain, if the domain is narrow in some direction, so here it's narrow, say in the x1 direction, lies in some narrow band, and if it's narrow enough, then you have the maximum principle. And it's easy again to prove that, but you construct a function g which is positive and satisfies the operator LG less than or equal to 0. A very explicit, simple function. Excuse me, my voice is a little bit hoarse. But thank you, yes. Yeah, thanks very much. A rather recent condition, I consider 20 years ago as recent. But for young people here, it's not so recent. But anyway, for me, it's recent. And it's a really and not a very classical condition. And it says you have the maximum principle in case the measure of the domain is small. Small depending on the dimension, on the ellipticity constant, and the bounds of the coefficients of the operator. And another not so classical condition is, suppose there is a function g which is just positive in the domain, not necessarily in the closure. It need not even be bounded, but it satisfies the inequality and not identically the equality. If you have such a function, then you have the maximum principle. So I'm going to use this condition 4, 1994, turned out to be a very useful condition. And I would also use what's called the strong maximum principle, which goes back to the 1920s due to Eberhard Hof. And it says, if you have a solution, sorry, I keep making mistakes. If you have a solution of this inequality, if u is greater than or equal to 0, it's the inequality the other way around. And if u is greater than or equal to 0 and happens to vanish at some point in the domain, then u is identically 0. And that is true without any condition on the coefficients. It's a very classical and very useful condition. In addition, I want to mention the Hof Lemma, which is this, which he published a number of, some 25 years later, although it's really as basic as the strong maximum principle, which says, again, if you have a positive solution of the inequality in a domain, if it vanishes at a boundary point, and if the boundary is reasonably smooth near that point, then the interior normal at that point is positive. That's the strong maximum principle. Of course, I don't expect you to remember all these, but at some point I'll refer to them. So now, let me take up the first, before I take up the geometric problem, I want to say the maximum principles apply also to a fully nonlinear operator. So it's a general function of the variable x in the domain, the function u, first derivative, second derivatives. Ellipticity means essentially that this matrix derivative of x with respect to the second derivative matrix is positive definite for all values, say, of the arguments. And the form of the strong maximum principle is this: if u is greater than or equal to some function v, and u and v satisfy these inequality, the nonlinear operator applied to u is less than or equal to that for v, and if u happens to equal v at some point, then u is identically equal to v. That's the strong maximum principle for nonlinear. It follows immediately from the linear strong maximum principle by just looking at u minus v, which we call w, and it satisfies a linear elliptic inequality, and then you just use the strong maximum principle. And similar thing holds for the Hof Lemma. Okay. The method of moving planes was introduced by a geometer, A.J. Alexandrov, in the 50s. It was to solve a geometric problem. And this method of moving planes, which he introduced, which I'll describe in a moment, has been used since then in a number of things. And it's really surprising how useful it turns out to be. He introduced it in 58, in this paper, uniqueness theorems for surfaces in the large, 1958. It's a paper in Russian. And here's the theorem that he proved in that paper. If you have a compact, smooth hypersurface in Rn plus 1, so the surface is of dimension n, which is smoothly embedded in Rn plus 1, and it satisfies the following condition. The mean curvature, this is the average of the principal curvatures of the hypersurface, is identically a constant, then this hypersurface is a sphere. If M is immersed, not embedded, but just immersed, many people try to prove it for the case of an immersed hypersurface, but then there was a counterexample. It was constructed by Wente in 1986. He constructed a two-dimensional torus which intersects itself in R3 and has constant mean curvature, and so it's not a sphere, it's a torus. A very interesting construction. Here's an expression for the mean curvature. If you have a graph of a function, if you have a function of n variables, x1, xn, u is the function, and you look at its graph, the mean curvature is given by that expression in terms of derivatives of that function u. So it involves second order derivatives. It's nonlinear, it's elliptic in the sense that I expressed before. The derivatives of this expression with respect to the second derivative, there are second derivatives there, should be elliptic, it's positive definite. And so here I've rewritten it again in this form. You see second derivatives occurring because they get differentiated here. So it's elliptic, and Alexandra introduced, he gave us proof using this method of moving planes. What he did was to prove symmetry of the hypersurface in any direction. For instance, I choose the xn direction, xn plus 1 direction, sorry, where the surface is a hypersurface in xn plus 1, and I'm going to show that the surface is symmetric about some plane, xn plus 1 equals a constant, lambda 0. So here you have symmetry above that plane. And this is done for any direction, and using the symmetry for any direction, it follows that the surface has to be a sphere. So here's how the argument goes for symmetry in the xn plus 1 direction in some plane. So I assume that the top of the surface lies on the plane xn plus 1 equals 0. And then I look at a hyperplane parallel to that, xn plus 1 equals lambda, which is negative but close to 0. And I look at the part of the surface lying above that hyperplane, and I reflect it in the hyperplane. There's the reflection. And this part of the surface, this region, I consider S lambda, and its reflection S lambda prime. Excuse me. And I look at lambda negative but close to 0. So S lambda prime lies in the interior of the surface. So the surface has an interior, of course, an exterior. And for lambda close to 0, the normal to the surface, it's nu is the normal. Its n plus first component is negative, so it's pointing down if you're near the top of the surface. And that's on the boundary, on the surface itself. And you start moving this plane so that there's a first number, this largest interval, so that I barely read it myself. I don't know if you can read it.
Star lambda holds.
No.
The largest interval such that star lambda holds.
So S lambda prime, so that's star lambda holds, that is, S lambda prime lies inside, still lies inside, and the n plus first component of the normal is still negative. So you move down as far as you can go, and then you are stuck. You'll reach some point, lambda 0, where you are stuck. I call it not lambda 0, but lambda bar.
No, you got one transparent.
So here's the picture.
Louis,
You move down as far as you can go, and then here,
Louis, you had a transparency before.
sorry?
You had one more transparency.
Oh, there's transparency.
Here.
Oh, yes, sorry, there's transparency before, excuse me, yes. So there are two cases to consider. One is where the reflection of the top part touches the surface somewhere here, where I've drawn it. And the other case is where the normal is no longer pointing down. Here it's still pointing down. But in this case, I'm going to show that this bottom part that was reflected from the top fills out the whole bottom, in fact. So here's the idea. Here's I look at the projection of the surface down on the plane. That's a plane, the x1 to xn plane, and it can be described by a function u, which is the height of the surface. So that's u, xn plus 1 equals u of the x on the bottom. And for the original surface, it's v, which lies below. So the u, the reflected surface, is greater than or equal to v, and at some point where it touches, u equals v. But there we have u as a solution of the mean curvature is constant, so it's equal to the mean curvature for v. We do have the mean curvature. So they're both solutions of the same equation. This elliptic operator for mean curvature equals the constant n times the constant mean curvature, and the w, the difference, u minus v, is positive, but it satisfies a linear elliptic operator. You just subtract the two equations, you get a linear operator for w. It's elliptic. Coefficients depend on u and v. You don't know what they are, but never mind. And u equals v at that point where you have contact. So by the strong maximum principle for the linear elliptic operator, u is identically equal to v near that point x0. So the two surfaces agree there. And then you continue to use the strong maximum principle, and you conclude that the two surfaces must agree everywhere. And so you have that the bottom half of the picture is exactly the reflection of the top half. So that gives you the symmetry, the desired symmetry. Case 2 is where you don't have that contact, but where the normal at the surface is no longer pointing down, it's horizontal. Then what you do is you just turn the picture around, rotate the picture. Here it is. Here's the original S lambda bar. Here is its reflection. And you look again at the surface represented as a function of u. Here's the reflected surface. Function of u satisfies the mean curvature equation equal to constant. And the original surface v, which now you describe as a v vertical here, and you have the same, you look at the difference, the u is bigger than the v again, and at the boundary their gradients are the same because the normal to both of them is the same. So you have solution of both satisfy w, u is bigger than v, except on the boundary u is equal to v, that is w is 0, and its gradient is 0. So it satisfies, w satisfies again the linear elliptic equation, which I think many of you cannot read. And the Hof Lemma says because the gradient is 0, that W must be identically equal to 0. So that tells you that this surface and that surface agree. So the crucial thing here is the Hof Lemma. So that gives you the symmetry. So the whole heart of the argument, there are two steps. One is the strong maximum principle, and the other is the Hof Lemma. And that's the heart of the argument. That just proves the symmetry. And that was Alexandrov's argument back in 58. What I would like to describe the various extensions of the Hof of the Alexandrov result were proved. I would like to describe one. Still have some time. Yeah. Due to Yan Li and myself, this was proved in 2000. And here is the statement. It says, look again at an embedded surface in Rn plus 1, and look again at the mean curvature of the surface, and assume that in some direction xn plus 1, that if you look at 2 points on the surface, one lying above the other in that direction, so here's A and B lies just directly above, and so the xn plus 1 component of capital B is little b of capital A is little a, and B is bigger than A. So the assumption is that at the top point, the mean curvature is less than or equal to the mean curvature at the bottom point. Assume this holds at any 2 points which lie directly above each other on the hypersurface. And then the question is M necessarily symmetric about some hyperplane xn plus 1 equals constant? Which would mean that the mean curvatures actually have to be equal at those 2 points. That was the question that we asked, and originally Yan Li had proved it under some condition, which I won't state, but here's an example showing that it's false in general. Here's a curve in the plane. There's a bump here and a bump here, and you have the mean curvature from A to B is the same value, same thing on the bump, same thing on the bump here, but this curve is not symmetric about some line x2 equals constant. So you need some condition. And we added a hypothesis, which we call condition S, which assumes condition S is that M stays on one side of any hyperplane parallel to the xn plus 1 axis that is tangent to M at 0. So here, M doesn't stay on one side. For instance, here it's tangent, but the surface doesn't stay on one side of that tangent here. So that doesn't satisfy that condition S.
Convexity would be enough?
Well, yes, convexity would be enough, certainly, yes. And so, in fact, that condition implies that the interior of M is convex in the xn plus 1 direction. This one happens to be convex in the xn plus 1 direction, but it doesn't satisfy that condition. So just convexity in the xn plus 1 direction is not sufficient. And the conjecture, it's a conjecture, so here's an open problem, the first open problem. Assume our main condition about this, which I go back just to show you the main condition, that 2 points, if one lies above the other, the mean curvature at the upper point is less than or equal to the mean curvature at the lower point. So assuming that, conjecture is that under condition S, that M is symmetric about some hyperplane xn plus 1 equals some constant. So that's an open problem. This is the first open problem. And I can barely read what I wrote. The conjecture is true if you have a curve, if it's a curve. So in other words, in the plane, if you have a curve satisfying condition S and the main condition, then the conjecture is true. And for n bigger than 1, the conjecture is also true if we added 2 other conditions. Alas, we need other conditions. One condition is, given any line parallel to the xn plus 1 axis that is tangent to the surface, it has contact of finite order. For instance, if the surface is analytic, that holds. But we need another condition, that at any point on the surface where the tangent plane is parallel to the xn plus 1 axis, near it, the distance to that tangent plane is convex in the xn plus 1 direction. So it's kind of strange condition, but we need that. So with these 2 extra conditions and condition S, we do have symmetry. But it would be nice to get rid of that extra condition, these 2 extra conditions. I won't describe the proof, it's a bit technical, it's a bit elaborate. I would describe, however, a one-dimensional lemma. It's an extension of the strong maximum principle. It says, suppose you have 2 functions which are positive on an interval 0a in 1 dimension. They're functions of a variable t. U is supposed to be C3, B is C2, U is greater than or equal to B. They're C1 in the closed interval, and at the origin, they both vanish, U vanishes, and both of them in fact vanish, and the first derivative vanishes. And either U is strictly monotone on the interval, or V is strictly monotone. E dot is positive or U dot is positive. And the main condition, as in the Hof Lemma, if at some pair of points U of t equals V of S, if they happen to intersect, then on some interval, the S has to be then greater than t, then at that point, the second derivative of U is less than or equal to the second derivative of V. That's the main hypothesis. Conclusion, U is identically equal to V. It's a funny one-dimensional lemma. The proof is simple, but not immediate, and I won't give the proof. But it's a kind of curious lemma. You see the picture there. Here the U is strictly increasing. I drew the V is strictly increasing. Didn't have to be. Proof, as I say, is somewhat roundabout. Open problem. Is there a higher dimensional analog of that? We don't know. So for example, suppose we have U and V are functions of a variable t and some other variables y lying in Rn. T is positive. U is greater than or equal to V. Say they're both C infinity functions. And we're looking at a domain which is sort of a half ball. So T goes between, no, it's rather a half cylinder. T goes between 0 and 1, and Y is bounded by 1. So we're in a half cylinder, and both are C infinity functions. Assume U is bigger than V, yes, and U, I should say, greater than or equal to V. They're both positive, sorry.
Yeah,
And UT is positive. U is increasing in T. And when T is 0, U is identically 0, and UT is identically 0 at the origin. And the main condition, wherever UT, so for some Ty, U is equal to V of Sy for some S bigger than T, then the Laplacian of U at that point is less than or equal to Laplacian of V. Question, is U identically equal to V? So it's a conjecture, and I don't know the answer.
But do you think it's true?
I think it's true, yeah, but I don't know the answer. So I wrote lecture 2 because at some point it was part of another lecture, but never mind. So I now want to move, the method of moving planes was then extended by different people after Alexandrov. Seren used it to prove a very nice result, and then Caffarelli and Gidas, it's not Caffarelli, sorry, Gidas and Diana used it to prove a symmetry result. So here, let me state the simplest case of symmetry result. If you have a ball in Rn, a positive function which vanishes on the boundary and satisfies such a simple nonlinear equation where f is a Lipschitz function, then this equation is radially symmetric, and the question which was open for many years is U radially symmetric. And what we did in, I forget the year, yeah, here's the year, 79, with Gidas and Ni, we proved that U is radially symmetric, and that U is, as a function of the radius, is strictly decreasing R, the radius between 0 and capital R in the ball. And we use the method of moving plane. And it only is based just on the maximum principle, and that condition for the maximum principle, that the maximum principle holds if you have small volume. Yeah, sorry. No, we used, in this paper, we didn't use that condition. We used a different condition. And we didn't know if the result held true in a cube, for instance. If you have a cube, I didn't draw a cube, let me go back. Instead of a ball, if you have a cube and the same equation, excuse me, oh, sorry. Question, if you have a cube, we have a cube and same equation, positive function vanishing on the boundary, same equation, we didn't know if the U was symmetric in the obvious symmetries for the cube. And that problem remained open for a number of years. And finally, it was settled using that result, that using method of moving planes, and the result that if you have a domain with small volume, then you have the maximum principle. So that was settled only in the 90s. And I'd like to mention some results using the method of moving planes. For instance, suppose you have a domain, suppose you have this, suppose you have a domain that's symmetric. Here's a domain, say in the plane, symmetric about the x1 axis. You have the same equation, U is positive, and it's 0 on the boundary. Then it's symmetric in x2. The method of moving planes shows it's symmetric in x2. You don't need a ball, you just need, if you want to prove symmetry in some direction, you don't only need convexity in that direction. So and the plane, you can do the method of moving planes, and it doesn't have, the plane doesn't have to move parallel to itself. It can move, for instance, a rotating plane. So for instance, in this picture we can move a plane, start taking that plane and rotate it, and prove that the reflection of that domain in here, that you have an inequality. For instance, in such a domain, which is, it's supposed to look symmetric, it doesn't look terribly symmetric. Again, if you have Laplacian U plus f of U equals 0, U is positive, 0 on the boundary, then the solution is symmetric about that line. And you prove it using moving a plane like that, and using monotonicity. So the method is a very flexible method, and I must say I'm surprised by some of the applications of this method of moving planes. It's a very simple method, and it's been applied to prove estimates, to prove uniqueness, and even, as I say, to get estimates. It's really a beautiful method. People are still using it. But here's a question. Suppose you have this domain. It's symmetric about that line, but it's not, I want to prove symmetry about that line. It's not convex in the direction where I'm trying to prove symmetry because you use that convexity. Same equation, positive function, u is 0 on the boundary. Question, is it symmetric about that line? I don't know. If it's narrow, then you take the solution here, you flip it over there, then you have two solutions in the equation, and you can compare them. They agree here, so the difference is 0 here, the difference is 0 there, and you can use the maximum principle if the domain is narrow. So if that angle is small, the answer is yes, you have symmetry.
Compared to F, right?
Sorry?
Narrow
Compared to the Lipschitz condition that F satisfies. But if it's not narrow, I don't know. And my conjecture is it's false. Yeah, my conjecture is false. If you have a big enough angle, my guess is it's false. So maybe some student can produce a counterexample. Very simple question. I'd like to mention also the sliding method, which was introduced by Berestiki and myself. It's also a way, it's not a way to prove symmetry, it's a way to prove monotonicity, and it's in some direction. Let's say I want to prove monotonicity in some direction.
X1.
X1, okay. Here's X1, yeah. And I assume the domain is convex in the X1 direction. That means any line parallel to the X1 axis, the intersection with the domain is just an interval. So assume that, and I would like to, assuming some, again, same equation, but u is not 0 on the boundary, it has some boundary value phi, and the main hypothesis is that if you take any such line parallel to the X1 axis, and you assume that the value of u at any point on the line lies between its values on the endpoint. So u here is bigger than u at the left endpoint and less than u at the right endpoint. That's the main hypothesis. Conclusion, u is actually monotone in the X1 direction, and u sub X1 is positive, and this assumes that f is a C1 function. So here you have monotonicity, and in addition, the solution u satisfying these conditions is unique. There is only one solution satisfying these conditions. And the way it's proved is again using, oh, sorry. Thank you too soon. That reminds me, in case I run out of time. I was once attending a lecture at Quran's Institute. There was a young Chinese, very young Chinese speaker, and he gave a talk, and Gromov was in the audience. And if you know Gromov tends to ask lots of questions. So he kept interrupting the speaker many, many times. And at the end of the talk, the hour was over, and the chairman got up and said to the speaker, "Your time is up." And this young Chinese guy said, "No, Gromov took 10 minutes of my time. I will speak 10 more." So Jagday took 10 minutes of my time. If necessary, I'll speak a few more.
Sure.
I think one more transparency.
Yes, I want to mention that transparency because it's a very, here, the proof uses by not moving planes, but it takes the domain and it slides it over, and it looks at the intersection, and it compares the original solution with, it compares the solution you have slid over with the original solution, and it shows that it's bigger than the original solution. And again, you look at the difference of the two. They satisfy a linear elliptic equation, and they have the right inequality on the boundary because of the condition, the main condition. And so by the maximum principle, the slid one is bigger than the other one if the domain is narrow. But then you keep sliding, it's not narrow, but then you argue using small volume, and you conclude that you get this monotonicity and uniqueness. And here's a very cute application. It's due to Cowell and Squeers. I think I've written their name somewhere.
Second line.
No, sorry. Excuse me. Yeah. So here is it's a rather poor picture, but it's supposed to have all the symmetries that you can imagine. So if you use the method, so it's again a solution of the same equation, Laplacian U, where is the equation? There it is. U is positive, it vanishes on the boundary, and notice it's convex in that direction, it's convex in that direction, convex in that direction. So you have symmetries by the method of moving plane. So at these points, the values of U are all the same. Here it's equal to that, here it's equal to that, here it's equal to that, here it's equal to that by the method of moving planes. But in addition, you have more symmetry. Look, you have symmetry about that line. Question, is the solution symmetric? For instance, is the value here equal to the value there? Method of moving planes doesn't tell you that because you don't have convexity in that direction. But they prove that it's true. You do have symmetry. And they use, in addition to moving planes, the sliding method. And so here's their argument. It's a very simple and very cute argument. They want to prove that the value here is the same as the value there. Namely, they want to prove symmetry about that line. And their argument is the following. Do the reflection. They want to prove, I repeat, symmetry in that line. Now, by the method of moving planes, they know that the solution is monotone increasing in that direction because we have convexity in that direction. We have convexity in that direction, so it's monotone increasing in that direction. They take the solution here and they flip it over onto here. Then they have two solutions, both of which are increasing in that direction, and they have the same boundary conditions, and by the sliding method result, there's uniqueness. So the two solutions, there's uniqueness. If you take the difference, it satisfies a linear elliptic equation, and you have this monotonicity in that direction, and by the uniqueness result that you get from the sliding method, the two agree, that gives a symmetry there. So it's just a simple application of the sliding method. Very lovely result, I think. So I'd like to conclude my talk with the following. One knows for the equation, our usual equation, the Laplacian U plus f of u equals 0, u positive, we know that in a ball, if u is 0 on the boundary, you have radial symmetry. Question, suppose you're in a half space instead of a ball. Here is a half space. Xn, you're in xn positive, u is positive, it's a solution of the equation, and vanishes on the boundary. F is, say, locally Lipschitz. Okay? So, conjecture. If u is bounded, if it's supremum is finite, then the u is just a function of that variable. So, that's just the analog. If you're in a ball, then u is radially symmetric. here the question is, if U is bounded, is it just a function of the xn variable? If that's the case, then in fact, necessarily the f of m has to be 0. So that's conjecture, open conjecture, very simple conjecture. Been open for some time. A number of people have worked on it. It's true in 2 dimensions. That's a result of Berestiki, Caffarelli, and myself proved in 97, I think, not so long ago. So we also prove it's true in any dimension if f of the supremum of U is less than or equal to 0. That was proved in 93. And there's some other open problems. I would like to mention those. Namely, here's another conjecture. Same as above, but don't assume that U is bounded. Do not assume U is bounded. Again, we have the same conjecture. Then, same equation of Gaussian U plus f of U equals 0. U is positive, not bounded, 0 on the boundary. Then, conjecture, the xn derivative is positive. U need not be a function of xn alone, but conjecture is the xn derivative is positive. So here's an example. For instance, in 2 dimensions, U equals y e to the x. It satisfies that equation. It's 0 on the boundary, y equals 0, and it's monotone in the xn direction. But of course, it's not a function of y alone. This conjecture is true in 2 dimensions, which was true only recently. The paper is still not published, in fact, by Farina and I can't read my own writing. Shulzi, yeah. In a very nice paper. And some years ago, Caffarelli and I and Berestiki looked at the equation, at this simple equation, thinking maybe this is a counterexample to the conjecture. For this equation, U is positive. Here's a very simple equation. U is 0 on the boundary. It's easy to see that if U is bounded, supremum is at least 2, which means that the f of the supremum is not less than or equal to 0, 2, at least 2 minus 1, at least 1. So that would be a counterexample. And our conjecture was no such solution exists. There is no solution. Bounded solution, positive solution of that simple looking linear equation, which is 0 on the boundary. No such solution exists. If there is a solution, you can symmetrize it about the xn axis and assume it's radially symmetric in the other variables. So it's just a function of 2 variables. Is there a solution? Conjecture, no such solution exists. But I've spent many hours trying to prove that no solution exists, and I don't succeed. So that's a nice, simple conjecture. I hope some young person here can settle it. And the conjecture is true in 2 and 3 dimensions with a very simple proof. And I believe I've used up my time. Yes, I believe my hour is up. So I will thank you all very much for your patience.
Questions or comments?
This thing about the hyperspace, would there be a possibility?
You mean half space?
Yes, half space. To use, let's say, conformal mapping into the case of the sphere.
Well, the equation isn't invariant. under conformal mapping. There are some special forms of the nonlinearity which are invariant, and a lot of work, for instance, Laplacian u plus u to the n equals u to the, I forgot the power, n plus 2 equals 0. That equation is conformally invariant. So for instance, there's a beautiful theorem that if you have a positive solution of that in the whole space with no condition near infinity, then it's radially symmetric about some point. That's a beautiful theorem of Caffarelli, Gitas, and Spruck. And then the method of proof is to do an inversion in a sphere so that things behave nicely at infinity, but then infinity gets back to the origin, and then you don't quite know what happens in the origin, so that's where all the work comes in. But the point is that equation is invariant under reflection, but the general equation isn't.
Thank you very much. You asked whether there is a higher dimensional analog for this beautiful 1D lemma about the identity of these functions u and v satisfying certain identities and inequalities.
No, we don't know any higher dimensional analog of that.
In the parabolic case, there is a nice theory called the Nagumo-Westphal-Walter theory, where instead of the inequality between the Laplacians, you have the inequality between the two Hertzian matrices, and then it works. When the difference of the Hertzian matrices is positive semi-definite.
But that's
that
for,
works.
but that's for that you're comparing the Hessian at the same point.
Exactly.
Yes. Oh yeah. That. Yes. Sure. But here, the whole point of the one-dimensional lemma I wrote down is that you're comparing the second derivatives at different points.
Sure.
Yeah.
I just wanted to point out, maybe when you alter the conjecture by using the Hessian, then there might be a hope to get an easier solution.
Well, that's a good question, and I don't know. I never thought about that.
I mean, for the parabolic case, it works, but of course, the parabolic case is much easier than the elliptic case.
Well, yes and no.
I mean, in the parabolic case, it works.
Yeah.
That's why
Okay.
it's easier. The proof is quite easy.
But there again, you're comparing the two functions at the same point, and in this one-dimensional lemma and in the question whether something holds in a higher dimension, you're comparing at different points.
Yes.
Maybe there's some parabolic version of that. I don't know.
I don't know.
I don't know. Anyway, it's an interesting question. Yeah. I should say that the strong maximum principle was proved, and the Hof Lemma for parabolic equation. In fact, the Hof Lemma was proved for a parabolic equation by Abner Friedman some years after Hof did it in the 50s.
Any other question or comment? Now we thank Louis again for such
Thank you very much for your nice lecture. The UBC University is really proud of having Professor Nirenberg here. Thank you very much for accepting the invitation made through Professor Xavier Cabrera, and also thanks to Xavier Cabrera. I just have to correct my former PhD student, Jaume, because Xavier Cabrera wasn't a student of this university, unfortunately, but he's a former student of University of Barcelona, where he studied mathematics when I was teacher assistant there, and Jabo, who was the professor of the subject, one of the subjects where I was a teacher assistant. With respect to what Uriol Serra, the director of the department, the head of the department said, some of the ambitious academic goals you put here on the table were already achieved from the Catalan mathematics group when this group get the Maria de Mez to recognition, acknowledgement. So this is important for the Catalan community of mathematicians, and I would thank all of the people that participated there because for having this. I think this allows here and acknowledge that in Catalonia there is a large community of mathematicians covering several fields of mathematics, and also at this university we have several people covering a lot of fields of mathematics. I would ask you, all of this community, to attract new students for masters and PhDs in order to such a day. Maybe one of them is Nobel Prize, or some of you professors here will be a Nobel Prize in the next years. And also another thing, the World University should take advantage of having this good and large community of mathematicians. And with this, I mean that all of the engineers should take advantage of this. I suggest you, the mathematicians, dance with an engineer in order to altogether obtain new results and better results that only one of these, the mathematician or the engineer, cannot achieve alone. Thank you very much to all of you for your attention, and thank you again, Professor Nirenberg, for your talk. Thank you.